Thanks a lot, Daniel. Let me just say the magic words that I would like to share my screen and hope that everything works fine, and it seems to do so. First of all, thanks a lot for inviting me to give this presentation. I think it's a huge honor, and I know Daniel since many years. Now it's a little bit strange when you give webinars because you never know who's watching there. But I will try to give this a little bit of a personal touch on my view of the room in the compositional space of electrolytes, and maybe less so exactly about the impact, but let's see where you might also bring it to. So I would just start by acknowledging the people, and this is not my research group. It doesn't look like that. This is a photo we took at the ECS meeting that was here in Gothenburg, where there's plenty of people from the Chalmers physics environment, past and present. The presentation I will give today is also not my own doing only. It's really heavily based on an upcoming perspective that I'm writing together with colleagues from Warsaw, from Barcelona, from Ljubljana, and indeed also from Uppsala. Daniel incorporated there as well. But I would like you to think about what can you present when you give a topic like this. I mean, it could be I had to figure out what I should do. Should I do a historical expose of the electrolyte development and where we are today in the compositional space? Or should I, knowing that most people that do batteries are not really into electrolytes, should I have a sort of like a more of a lecture of properties and the roles of electrolytes in the battery? Or should I only focus on the electrolyte state of the art and beyond, which might come as the most natural one? And I early decided that I will do something like is a mix of everything, giving me a lot of freedom. But I also know my own limits, and one of my limits is that I absolutely do not do solid state electrolytes based on oxides or sulfides. So that it will not be. It will be let's say, more classical electrolytes than the solid-state electrolytes that are very popular to talk about today when it comes to all solid-state batteries. So that will not happen. So anyone who's only into that, you can just tune out and do something else, I guess, or just have a bit of another exposure to something else, something different. But I would like you to take you back a little bit in time. I was a PhD student. I went to my very first IMLB conference, 1988 in St. Andrews, organized by Colin Vincent and Peter Bruce, who at that time was at St. Andrews. And it was a 5-day conference. And when coming there, I discovered, or maybe a little bit earlier, that from an electrolyte perspective, there were 3 days of cathode materials, there was 1 day of anodes, there was a half a day of electrolytes, and a half day of cells. And that sort of, and even the electrolytes was very much about interfaces and SCIs. So this was my first conference that was really a battery. And there was a disconnect, I would say, between electrolyte and battery community. I've been to conferences which dealt with electrolytes, solid-state ionics, polymer electrolyte meetings, etc. And there you don't really do cells and electrochemistry that much. You do a lot of physical chemical characterization. I think that comes from that you have a little bit of different experimental and modeling approaches, and you use different tools, and you also come from different trainings. That sort of sometimes leads to a blame game. It's always someone else's fault. And I think we are, not exaggerate too much, but I think we're still a little bit hampered by this. Many groups have started to do everything, which I think is a great development, but that also means that you might spread a little bit thin. So I think this was a discovery that some of you that are electrolyte people might discover, but you might, maybe someone has not put words on it. But I think this was a true first thing, just discovery at that time. And I think things has become much better, but still, I think it's a reflection that sort of underlies what I will talk about today a little bit. So what's really needed when you go for a classical electrolyte? that you want to have in a battery? Well, you need one or more salts, you need one or more solvents, and you need maybe a bunch of additives. Doing so, you get a high ionic conductivity. The part of the ionic conductivity that you really care about is the cationic conductivity, because that's our charge carrier of interest. You also would like a wide electrochemical stability window so that you can make cells that has a high voltage window as well. And that means that your cells, you don't need that many cells to produce a high system voltage. You also want inertness versus the electrodes, and that means also that the electrode materials should not dissolve out into the electrolyte. It's not only about that the electrolyte should not react and decompose. And then you have other properties, like you want them to be non-flammable, you want them to be non-toxic, you want them to be inexpensive, and many of you know that that is not at all true for all electrolytes, far from it. But there's a long list of things here that you want. And doing that, then you can start to play around, and you can create a list like this. I think that some of you might not even find your electrolyte composition or type your favorite, but some other ones of you might be overwhelmed about the number of different electrolyte concepts that are on the screen right now. But one can organize them a little bit better, perhaps. So this is an attempt to make a map of the electrolytes and combine them in, for instance, trying to figure out what is salt-rich versus solvent-rich electrolytes. So highly concentrated electrolytes, meaning really highly concentrated in salt. Molten salt electrolytes being based only on salt being mixed together, etc. So there is really a way to organize electrolytes in some way, and you can combine them as well. And when it comes to battery technologies, which is really in the title of this presentation, the impact, one should note that some battery technologies are extremely limited in what electrolyte fits them. I can take as an example aluminium batteries. There are very few aluminium batteries, those that are based on inorganics at least, that work with anything else than with ionic liquid-based electrolytes. Lithium sulfur electrolytes are very special in the sense that you need to stop the polysulfides from transporting. So some battery technologies can work with almost any of these electrolytes, given that you have also the flexibility of chemistry in the two electrodes, but some of them are again very limited. I will, of course, not talk about all these electrolytes, then we will stay on for a few more hours, but I will make a small selection and just pick 7 of these electrolytes. Some, the liquid electrolytes, very traditional, some little bit less traditional, talking single ion conducting polymer electrolytes, but also staying quite some time on highly concentrated electrolytes and some derivatives from them, because it's been a trend now for something like 10 years to really talk about what happens if you put a lot of salt, the salt-rich electrolyte concepts into your solvent mix of preference, and what happens then. So it's really going to be a lot of focus on that part of the electrolyte chart. So talking about solvent-free electrolytes, or at least free solvent-free electrolytes, is it really a target name also of the solid-state electrolytes? We're talking oxides, sulfides, or whatever. And how could you accomplish that here when I said that we're not going to go on the crystallized? Well, traditionally, we have the solid polymer electrolytes and also the composite polymer electrolytes, which really has no traditional solvent. They've been based on having a polymer inside, the composite polymer electrolytes also with some kind of nanoparticles inside. Popularized early by Michel Amand and now late Bruno Sgrosati, big loss to the community, by the way, and also being commercialized, the solid polymer electrolytes, by companies like Blue Solutions. You can also do it with ionic liquid-based electrolytes, where you have no organic solvent, you have an ionic liquid instead. And here we saw the development early by Hikari Sakaebe, Stefano Passerini, Masayoshi Watanabe. And also here we have companies like Solvionic really living on selling ionic liquids and those electrolytes that you can build upon that. But I would say those are maybe the more commonly known ways around not having solvent. Molten salt electrolytes and liquid salt electrolytes, which I will talk about a little bit later, is really, they also have no solvent, but it's a little bit uncommon path, and maybe you need to go for higher operating temperatures. And as far as I know, there is no real battery companies or component companies that actually live on selling this. But then the main thing then, highly concentrated electrolytes, and the special case of having water as the solvent, being then water in salt electrolytes. These are not solvent-free, but they have very little or no free solvent, meaning that the solvent itself is very heavily coordinated by the cations in the electrolyte. And we will talk a lot, and that's also where my background comes from, talking a lot about what is the coordination in the electrolytes and what happens inside the electrolyte, etc. And how does that then materialize at the global level. So starting off this schematic about highly concentrated electrolytes, just to bring you onto the page of how does a conventional lithium-ion battery electrolyte look like versus a highly concentrated electrolytes. So if we take the first case, we have about 1 molar of salt. We have very well defined, at least to a rather global picture, solvation shells. We have some ion pairing, absolutely, but we have very few larger aggregates, meaning that you couple cations, solvent, anions into a big chunk that moves together, for instance. And you also have a lot of free solvent available because your concentration of salt is quite low. So there's a lot of solvent that only moves within the range of other solvent molecules. As opposed to this picture, if you go for highly concentrated electrolytes, you go far beyond 1 molar of salt. You get quite a diversity of solvation shells. And here we're trying to draw up a little bit of what they can look like. And many of them are larger aggregates, things that stay together for quite some time. And there is very little or no free solvent because the salt concentration is so high, meaning that the cations can actually coordinate up all the solvents in place. Now we're changing the chemistry in the two pictures here, taking the ECDMC on the left and the acetonitrile on the right, but it doesn't really matter. It's just maybe a way to more easily visualize what goes on, but it's not really chemistry related. It's more conceptually related in terms of salt concentration. So how can we understand these highly concentrated electrolytes and what actually differs there? Well, one thing that really made them make it, sort of why people got very interested in them, is that you do change things. The widened electrochemical stability windows. Where does that come from? Well, if you think about a normal electrolyte, a liquid electrolyte, a conventional one at 1 molar, basically, you have these electrochemical stability waves. You have the redox potential and you have the oxidation potential of the anion, the salt basically being the anion in this case. You have maybe 2 solvents, and they are additive in the narrowing range, meaning that if something is being reduced at the high potential and something is being oxidized at a bit lower potential, that is what limits your electrochemical stability window for a conventional liquid electrolyte. But if you go for a highly concentrated electrolyte, the picture of these components being individual species breaks down because of this aggregate picture. And that means that for a highly concentrated electrolyte, there is no real way to predict how it actually will be. But what was found early was that, okay, so you get quite a bit wider electrochemical stability window. You also get quite a bit of a different SEI, being more based on inorganic species. Not so surprising because you have so much more inorganic components in your electrolyte mixture as you're having much more salt than you're having solvent all of a sudden. And this really puts emphasis to highly concentrated electrolytes. So that's one thing that really makes them interesting. But can we do something else? Well, one thing that we started to do was to really try to figure out what is actually moving in these highly concentrated electrolytes. If we have these very diverse local coordinations, and we have aggregate formation. So clearly we have something else than just the vehicular transport. There must be something else there to be found. So we started to build a tool to look at molecular dynamics simulation trajectories. So we take a just conventional MD simulation trajectory, and then we start to analyze them in terms of what actually keeps together during a lifetime. And what's now called bond in this center part here is really a dynamic bond. It's a dynamic structure, but it keeps for some time before this aggregate really breaks down. And if you do that for each time step in a simulation, which then can typically be a part of a femtosecond, you can create a time-dependent bond graph. And with that statistical physics, you can start to talk about the distribution in terms of lifetime. You can talk about transition states between different species. You can talk how these, knowing their distribution and the transition rates, you can start talking about how do these actually contribute to the ion diffusivity that you see, and what is the mobility contributions, etc. So we built this as a small toolkit. It was a collaboration also with Alejandro Franco in LRCS in AMEA. And from that, we also spurred a spin-off company that now has 11 employees, just based on actually, or just, but based on actually trying to figure out what is moving in highly concentrated electrolytes. And this is a tool that one can use also for conventional electrolyte. But for this one, it was really crucial to actually bring it to this tool, to actually being able to find this. And what can we do then? Well, we can take any electrolyte. We can take conventional electrolyte like LP30. We can take various concentrations of LiTFSI and acetonitrile. We can create solvated ionic liquids as LiTFSI in tetraglyme at the 1-to-1 ratio. We can see what happens if you mix anions. And then you can see what are the dynamically present. And I would like to stress that these are dynamically present. So you see what is present just at these time steps when they are alive. And you can see how that varies as a function of electrolyte composition. And once you have this very local picture, you can also see things like how do things contribute to the dynamics and the transport. And especially interesting, of course, is to see, as we're talking about how highly concentrated electrolytes are different, do they have a vehicular mechanism, which we truly believe that they did not. So the thing which is here a little bit darker is really the vehicular mechanism. And the ones that have a lighter shade of the bars is the non-vehicular mechanism, so basically jumping or collective motion or something. So you see, even for LP30, which people would arguably say, yeah, it's mostly or only vehicular mechanism, you see that actually there's quite a bit of contributions also from jumping or non-vehicular mechanism. But of course, as soon as you go to highly concentrated electrolytes, this non-vehicular mechanism really starts to dominate. So you really can tailor your electrolyte based on this, knowing these things, and you can see how the system reacts to the choices of different solvents and different salt concentrations, etc. You're not limited in any way to find out for this. So that's one way to do it. Why only look at one way to address the dynamics? Another PhD student of mine, Gustav, he thought that, well, this thing with molecules is a bit complicated. Let's simplify the molecules, both solvents and anions, into centers of mass, and look at how these things move together versus a cation center, and really saying that forces in an electrolyte solution are stochastic, and the forces will determine the dynamics. And then you can get ligand exchange rates. So we can talk about how things evolve around a cation, both anions and solvents. How do that change from these random forces and the velocities that you have there? I will leave the mathematics behind a little bit, but just to show you how we use it to actually study what happens for different types of electrolytes. We'll show you 6 different electrolytes and show what that happens with that one. So But first of all, talking about what we're really showing here, we're taking a proof of concept, nothing really fancy. We have a 1,000 atom CPMD simulation, and we're doing that for differently concentrated lithium or sodium PF6 in propylene carbonate or acetonitrile. And basically what you will see is on this distance from the cation, you will see basically the signatures of the first solvation shell and the second solvation shell of the cation, with some probability and some radial force. We can leave that behind, but basically the probability is the most important because that tells you how probable is it that you have a solvent molecule or an anion at that distance from the cation. So if we go now, and this is only solvent data, just because that even if we go now for, you'll see in the small print here, it says 20 to 1, 10 to 1, 5 to 1. So that's the molar ratio. So we have 20 more solvent molecules than we have PF6. So it's basically the solvent data just to get better statistics. But what you can see if you go from top left down on the LiPF6 in concentration, one sees that it gets a little bit closer between the solvent shells. The lithium, though, if one compares the leftmost to the little bit to the right, one sees that moving from lithium to sodium, it gets not at all as structured as it gets with lithium. Not surprising. Lithium then would organize its solvent shell much harder than the sodium will. But really, there is also for the sodium case, there is an exchange between the shells. You see that the probability, especially for the highly concentrated, that you have species in between the shells. And that really means that you have a solvent exchange now. So you have some kind of dynamics between the shells. And having that knowledge that you have that and the mathematics behind that, you can actually start to look at the residence time of these solvents. And then from this system, we also developed a new equation for the residence time. And then one can see that when you go up in concentration, creating a highly concentrated electrolyte, you move from lithium to sodium, you get a shorter residence time. So that means that you have a faster exchange for sodium than you have for lithium for the highly concentrated electrolyte, which is really what you actually see. You see that sodium-ion batteries and their electrolytes, they have more improved kinetics, not only in the bulk. Now we're only in the bulk here, but the overall batteries do have good power performance, for instance. And this then correlates with that. I'm not saying that there is a strong causality, but you really see that it correlates well with it. That is so, and not too surprising, but nevertheless, it's nice to put numbers on it. So that's two different ways to address highly concentrated electrolytes by simulations. A little bit different stance is the high entropy electrolytes. That is something that maybe the last 3 or 4 years, and it was not among the electrolytes that I was listing, has become very popular in the literature. Buzzword. Is it a buzzword? Is it not only different cation solvation? Well, depends on what you mean here. If you're talking about liquid electrolytes, where you basically have a solvent mixture, it's not only that it's true that you have a high entropy in your electrolyte, but less common though is deep eutectic electrolytes or molten salt electrolytes. And there most often you do actually have true high entropy electrolytes. And what do I mean by true or not true high entropy electrolytes? And I mean, I'm not saying a perfect true or false here, because there's always exceptions to the rule, right? But if we go for what really happens here, if we start with molten salt electrolytes, what is a molten salt electrolyte? Well, we start with a conventional salt. Think about your favorite lithium salt or sodium salt. Basically, when you're starting to think what happens if you start to mix that with something, you would have a delta G mix. But if you take two salts and mix them together, then the entropy of that system will increase and your free energy of mixing will decrease. And then you do that for a number of more components, and you will see that at some point your melting point goes down to a temperature perhaps where it's getting useful. So by this, you can in principle create something which is a solvent-free system. These are not really solids in the sense of macroscopic properties. They are maybe something that is liquid in a true sense, but they are also quite sturdy. So let's call them semi-solids on the macroscopic scale. And they do have a density of, if it's monovalent or divalent cations, which is somewhere in between what a conventional liquid electrolyte and a solid-state electrolyte. It's actually quite much closer to a solid-state electrolyte charge carrier density in terms of volume. And that's, of course, very important that you actually have quite a lot of the species that you are interested in. So we've been doing a little bit of that. So one of my PhD students and one of my postdocs have been doing some simulations and some experiments using FSI salts, and nothing complicated with that, but mixing up to 4 different FSI salts with different cations and studying then what happens with the melting temperature. And in the center here, you see that if we go from binary to ternary to quaternary, one can see that the melting point is falling down and the entropy of mixing is going down. And that is really what we want to accomplish. We want to accomplish something which, of course, ideally would be liquid at room temperature. Here we have systems that are melting at 54 or even lower for some of the ternary ones. And we can see that this is really a way to create high entropy electrolytes. Are these stable then? Well, if you look at the Raman spectra on the very rightmost here, so the ternary ones, they do have a development with time. After 1 week after we cast the systems, they start to develop a structure. That means that they're probably metastable. Of course, the dynamics of this system is very slow. They're very high viscosity and they're very dense. But if we look at the one to the top here, after 1 week, basically the Raman signature of this anion peak that we selected as a probe basically stays the same. And that means that we do actually have a stabilization effect here of the entropy. So there's an entropy stabilization effect. So that means that the local structure more or less stays the same over that time frame. 1 week is not a long time, but nevertheless, with maybe also if one gives it a temperature push, it can go 2 ways. Either you can start to crystallize out, or you can again create a more liquid system. That's not obvious at all what happens when you do that. It's also so if you take only a modeling approach and looking at what happens with this system from a molecular dynamics point of view. Well, normally you start to talk about coordination shells, and also for the highly concentrated electrode, we said that, okay, but there is no free solvent. I mean, here you have no solvent at all. So the coordination shell, you cannot talk about coordination shells because everything is ion. So really the concept of coordination shell really breaks down. But something that is very obvious is that normally if you have an FSI anion or a TFS anion, you would see a lot of bidentate coordination by spectroscopy or by simulations. But here, almost everything is monodentate because that you can have a sharing of coordination across different cations. And so it's much, much more probable to have monodentate. And of course, that will also then affect the dynamics of these systems in a completely different way than a liquid electrolyte would behave. This is very much ongoing work, which I think is highly interesting to see the results of. One can also play around with actually adding even more things into a system like this. You can take a single salt or multiple salts. Here we're taking a single lithium salt and we're adding a hydrogen bond donor to protect the eutectic. So basically creating a DEE. So deep eutectic electrolytes. And here it's very obvious so that if you change the anion a little bit, you can actually create very much homogeneous systems or things that are on the molecular level quite different locally. So they have a low molecular level heterogeneity. And that actually is not only structurally so, but also dynamically. Depends on where you are around the lithium the anion and the hydrogen bond donor, where you are around those affects your dynamics of the different cations and anions. And that is also very much ongoing work, but I think that doing these mappings of this spatial distribution of both coordination and dynamics will give a lot of interesting information. And these are very highly concentrated systems as well, just to make sure here that people understand that here we're talking 4 hydrogen bond donors towards a single salt. So we're basically still in a very high salt-rich regime. Let's take another different angle to this thing with highly concentrated. Couldn't we use water as solvent? Well, yes. It's been a true revival for water as a solvent in the electrolyte world. But I mean, why should we not use it? Well, I mean, it's a safe, it's a non-toxic, low cost, ideally, yes. Water is low cost at least. Very abundant, and it's also very well-studied electrolytes. I mean, it's the oldest electrolytes we know, of course, are aqueous ones. But of course, also, maybe of course, we have a limited electrochemical stability window. We know that from, for instance, the fuel cell business. There might be solubilities of the active materials of your electrode. And the concentration of salts needed to mitigate that, if we're talking water and salt electrolytes, launched some 10, 15 years ago, we're talking electrolyte concentrations of 20 molar or so. So if you're talking that kind of salt concentrations, that's why there is a question mark on low cost. You have quite a lot of salt inside. It's rather that you have salt rather than water. And not to only say that, but it's also very common so that it's heavily fluorinated salts that are used that are rather expensive compared to other salts. But there might be ways around this. So this was a collaboration within the Destiny program between Collège de France, John and Alexis, and our group here. And we started to talk about, can we make aqueous organic batteries? So basically we have this PCTDI as an organic electrode, which then can coordinate up 2 lithiums. And we put that towards the LFP. So we're creating basically a pseudo half cell in this system. And we're looking at what happens if we go for the 1 molar LiTFSI solution or a 3 molar or actually a 5 molar solution. So you can see that we can actually cycle these quite nicely at the 1C rate, so admittedly rather fast. But still you see that this actually works for quite a number of cycles, rather good Coulombic efficiencies. And if we go up and actually go the further step, not a pseudo half cell, but actually creating a full cell with an LMO. And now remembering now that, of course, for aqueous systems, we know that manganese dissolution is a problem. So with a 5 molar lithium TFSI, we can see that we can actually cycle with a decent capacity retention, an aqueous full cell based on this PCTDI and LMO cell. And of course, the advantage with this, I mean, of course, it's a bit of an explorative study. But the thing is that 5 molar LiTFSI is actually quite much lower than a conventional water and salt electrolyte salt concentration. And with that also, it's lower in cost. So as an example of what one can do. But one does not have to stay with these expensive salts. One does not have to stay with lithium. This is a very recent paper together with a former postdoc of mine, Rosa, who's now working in Max Planck in Germany, in Golm, where we start to look at zinc electrolytes and playing the game of cosmotropic and chaotropic anions. So cosmotropic and chaotropic basically mean structure creating or structure destroying anions. And what we're playing with here is actually that the acetate can create a good environment around it. So that's an anion that is cosmotropic. And then we're adding into the system a guanidinium cation, which is a chaotropic anion that actually creates disorder. And it also changes the local concentration. So when we're finding a good electrolyte balance between a zinc salt and a gadolinium salt. So basically mixing zinc chloride with gadolinium acetate in a sort of like the magic number mixture after quite some attempts. We see that we can cycle a cell quite many cycles with a reasonable speed, etc. A small coin cell, zinc vanadium oxide coin cell. We see that we have now a weakly solvated electrolyte. What does that mean? That means that the zinc is not very strongly bound to anything, so it becomes rather mobile. And we also see that how we do change these things, both by simulations and by a lot of spectroscopy. We can see that this is what's happening locally in this structure. And that is what really is the secret behind getting these performances that we get. But of course, not everything is water. Can we do, I mean, we were at something that was non-fluorinated now. Can we make a non-fluorinated liquid electrolyte? And now I say even LSE. What is a LSE then? Well, liquid salt electrolyte. Before we were doing this molten salt electrolytes, we were mixing several salts to get something liquid. But here we're actually going for a non-fluorinated liquid salt, which is liquid at room temperature. So basically, we avoid the fact that having the conventional thing is to have heavily fluorinated anions, because we want them to be weakly coordinating. We want these wide electrochemicals to windows. We want the source of fluorine to passivate the aluminum current collector, which is actually one main reason to have these salts. But we do take the advantage of cost, the environmental effects, including recycling, very complicated with fluorines, and also the degradation of the electrolyte. So we basically created, this is a collaboration with the group up in Luleå in Sweden, created this phosphate-based lithium salt. Some lithium salt, sodium salt, potassium salts. And the thing is that here we create something that I would say conceptually interesting, because we really just having a salt, one single salt being the electrolyte, but at the same time the battery performance is perhaps not so great. And then for those who question this, is this really a salt? Yes, there is no liquid in it, and it actually has a flow, not super low viscosity, but it does have a flow even at room temperature, as you can see in the small loop. So we're minimizing the number of materials that we use for the electrolyte, but of course there is a lot of development to be made here, both in terms of electrochemical stability, etc., etc. We don't have the fluorination, which might be something that we want to add in the end anyway. And if we're going for the thing with, now we're having non-fluorinated, but if we go for heavily fluorinated liquid electrolytes, why would we do this? So here I would like to showcase another collaboration within the Destiny framework, and that is together with NIC in Slovenia, with Sarah and Robert, and especially the work of Ahmad. And here the argument really, why would we use heavily fluorinated electrolytes in some way? Either it's as a salt or an additive, as here it's a solvent. Well, the thing that people don't necessarily recognize is that if we're going to go for 800 volt or 1 kilovolt battery system in an electric vehicle, that means that high voltage cells are going to have a lot of advantage to anything that is less voltage in the cell. And here we do that by having a CI forming additive. So thinking that, okay, we will have a high voltage electrodes. In this case, we do it with NMC 811, and we see what happens if we take a few of these fluorinated additives. And it's not as easy to just bring in a fluorinated additive. It's not that easy to just play the game of just having this concentration or that concentration. But here it's actually several things. We do go from 1 molar to 2 molar of LFSI in the solvent mixture of DME together with the BTFD, the cyclic fluorinated ether. And we see that we get a much improved performance, not only by the chemistry, but also by this compositional space of adding twice as much as solvent. And I would say that here we really see the performance in some kind of relevant battery test. I know that relevant is always up to the beholder, and here Sure, yes, we might have maybe a bit too much electrolyte for your liking, but we do have quite a sensible loading. We're using NMC 811, etc. So it is reasonable in some cases, at least, talking about really performance of a lithium metal battery in this case. So it's not designed as a half cell. It's really designed to be a lithium metal battery, but with a liquid electrolyte. The final example I would like to give is almost coming back to where I started from more than 30 years. We're making polymer electrolytes and seeing more or less what happens if you mix things together. So quite often, what is the main question when do this really like how do you optimize the ion conduction mechanism versus the composition and mechanical properties? You want a polymer electrolyte that has some mechanical stability. At the same time, you want conduction, etc. So here we did a bit, me and my postdoc Laura at the time, we did a bit of a different take. We said that, well, you have these single ion conducting polymer electrolytes. They might not give you everything. But what happens if we mix those single ion conducting systems with a little bit or quite a lot of it, in the end, of a lithium salt? So we're not adding any solvent to the system, but we're also going away from the single ion conducting properties. So as you see here, we do not really make battery tests, but we're really probing the grounds of what happens with the coordination of the anions, what happens with the resistance at the in terms of impedance spectroscopy. Where would you really go when it comes to the LiTFSI content, and what happens with the mechanical properties, etc. And that is sort of, I would say, it's an exploratory phase, which is not to be forgotten. Not everything has to be true battery tests. And you can see a lot of things happening when you do these kind of experiments, and especially this thing with what happens with the conduction mechanism, etc. It's very much up in the air still. So I just leave you with that as a sort of like, okay, what would happen here really in the truth. And now getting a little bit closer to the end of the presentation, I would just my take on future electrolytes. I really think that semi-solid state electrolytes have the future for them. Exactly in what shape, I don't know. The advantages with them is that they are as safe as solid state electrolytes, as they cannot basically leak in the same way. They are not flammable. And you would probably have less problems with interface and production. Question mark on that one, because how would you fill a cell, etc.? It's not obvious, and there might be good advantages for solid-state electrolytes as well here. So not want to discard them, but my personal take is this is interesting. Something else that I didn't touch upon at all, but there's coming quite a bunch of interesting papers out that is in situ generated electrolytes, where you start with one component and then you generate the electrolyte once the final electrolyte nature you generate once you actually filled your cell. And the decoupling of the very formulation and filling before you enter it into the cell from the functionality that you have inside the cell. I really think this is an interesting concept to be used. You can think about polymerization. You can think about other ways to do it, really, to generate these electrolytes, having reactions inside your cell. Of course, it's very early development, but I think it's conceptually interesting. What happens with fewer components versus entropy-designed electrolytes? Well, I mean, we do these molten salt electrolytes where you mix a bunch of different lithium salts. There's quite a lot of things that can happen as soon as you have many components. If you can make a single lithium salt, which is liquid, or a sodium salt, which is liquid, that might be advantages. But the question is, can it fulfill everything? So lower complexity is an advantage, but the question is maybe one can find synergies by mixing many things instead. So there's probably a sweet spot somewhere there in between. But this way of at all avoiding or at least limiting solvent and playing the game of salt-rich electrolytes. I really think that's an intriguing way forward. If it's 100% salt or 99% salt, let's see where the future brings us with maybe some diluents, etc., into the systems. And then, as it become a tradition when I give presentations, is the paper that I'm most proud of having written for myself and also from my research group. Something that took us a long time to write. It was a slow-moving effort for about half a year. And I think that the response by the community was great. And for those of you who not read it, I do, even if it's blowing your own horn, it's a little bit like, I think that it's nice. It's a nice paper, and I would recommend people reading it. And with that, I would just like to thank you all for your attention. I'm ready to answer questions, should there be any. Thank you a lot for listening.